In this video, I'm going to go over how to simulate a reaction design problem in Aspen. The problem that I'm going over is an adiabatic liquid phase isomerization of normal butane. So normal butane, C4H10, is to be isomerized to isobutane in a plug flow reactor. Isobutane is a valuable product that is used in the manufacture of gasoline additives. This elementary reversible reaction is to be carried out adiabatically in the liquid phase under high pressure using essentially trace amounts of a liquid catalyst that gives a specific reaction rate of 31.1 inverse hour at 360 K. The feed enters at 330 Kelvin. You're given some additional information like the heat of reaction and the activation energy. And we have three goals. The first goal is to calculate the PFR volume necessary to process 100,000 gallons per day, or 163 kilomole per hour, at 70% conversion of a mixture of 90 mole percent N-butane and 10 mole percent I-pentane, which is considered an inert. The second goal is to find out what the maximum conversion is for the PFR. And the last goal is to calculate the CSTR volume for 40% conversion. So now I'm going to head over to Aspen. All right, so this screen is what you should see when you first open Aspen. You might not have recent models, but on the left-hand side, you're going to select New. And on the left-hand side again, at the very bottom, you're going to select User. And then select General with Metric Units. And then select Create. So this is going to open up a brand new model. On this screen, you can insert your components for your reaction. This is called the properties area. So we have three components. We have N-butane, we have isobutane, and we have I-pentane, which is called 2-methyl butane. If you don't know the exact name, you can use the built-in search database to find your exact components. For component ID, which is kind of like a nickname, I'm going to name them N-but, isobut, and I-pentane. All right, you know when you're done with a page when there's a little blue check next to it. And Aspen's really great about walking you through everything that needs to be done, everything that's required to run your simulation. And to do so, you just press this blue next button. So it brings you to the next thing you need to fill out. And this is the method that we want to solve our problem. It tells Aspen how you want it to calculate the physical properties. Since we have a hydrocarbon liquid phase mixture, we will be selecting the Peng-Robinson method, which is called Peng-Rob. And as you can see, this is all we need for this page. So I'm going to click Next again. All right, so this is everything we need for the properties input. As you can see in the bottom right-hand corner, required properties input complete. So now I'm going to select Simulation. This opens up a flow sheet where you can add all sorts of things like separators, reactors, columns, and all sorts of things. But first, we are going to be entering in our reactions. So on this left menu, select the reactions folder and then select New. So I'm going to leave it as R1, but you can name this reaction set whatever you'd like. We have a reverse reaction, so there will be a forward reaction and a reverse reaction, or a reversible reaction, so there will be two reactions. For the type, it will be a power law. All right, under the stoichiometry tab, press New. And first, I'm going to define the forward reaction. So the reactant will be N-but. the product will be isobute. And for the reactant coefficient, it should be -1. And the exponent will be 1. For the product coefficient, it should be 1. And the exponent will be 0. Once I'm done, I'm going to press this blue next. And I am going to press new again to create the reverse reaction. So the reactant this time will be isobute, and the product this time will be N-bute. The coefficient for the reactant, once again, is -1, and the exponent is 1. For the product, the coefficient is 1, and the exponent is 0. So now I finish with stoichiometry, I'm going to press next. And it brings me to the kinetic tab. So this is where we define the reaction rate constant and activation energy. So as you can see, the forward reaction is selected, and we are given the K for that as 31.1 inverse hours. But I am going to change it into seconds, which was found to be 0.008639 inverse seconds. Similarly, I am changing the activation energy to be 65.7 e to the 6th, or 6.57 to the 7th joule per kilomole. And we know that the reaction is occurring at 360 Kelvin. Units are really important, so make sure that you have selected them correctly. So now in this top pull down, I selected the second reaction, which is the reverse reaction. And since we are given the heat of reaction and chemical equilibrium constant, we can find that the rate constant for the reverse reaction is 0.003442 inverse seconds, and the activation energy is 7.26 to the 7th joule per kilomole. And once again, the temperature is 360 Kelvin. All right, we are done with the kinetic tab, so I'm going to press next. And it brings us back to the flow sheet. So now we're ready to bring in our reactors. So under the reactor tab on the very bottom, we need a CSTR and a PFR. So I'm going to pull a CSTR into the flow sheet, and our plug is the PFR. So I'm going to pull that in as well. I'm going to rename them and drag it on top. And next, I am going to add a manipulator block under the manipulator tab called a duplicator. So what the duplicator does is that it duplicates a stream going into a block. So I'm going to be putting a feed stream going into the duplicator, and the duplicator will duplicate that feed stream into both the PFR and the CSTR. So I don't need to fill out the conditions for both streams into the PFR and CSTR. I can just do it for into the duplicator, and that will automatically put those conditions for the PFR and CSTR. So as you can see, there's little red arrows and blue arrows. The red arrows are required streams, so you need an in and out stream, and the blue arrows are optional streams. So next I'm going to add the product streams going out of the PFR and CSTR. And now I'm going to rename all the streams. So for stream 1, I'm going to name it the feed stream. For 3, it will be the feed to the CSTR. For 2, it will be PFR. For 4, I'm going to name it PFR for product. And for 5, it'll be PCSTR. So now I've made my entire flow sheet of everything that we need, and I will begin to assign parameters and values to the different blocks in the next video.